Okay, in the last video we discussed the idea of making a machine that could make universal or infinite graph paper. We can start by imagining a machine that can generate the graph paper for all the Brovais lattices. It's not that hard to do. We just start with a number line. Let's say we put our finger on 0 and we push a button that says plus, plus, minus, 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 plus, 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 plus. So you can see it's easy to control a machine to put dots in space on a line just by using operators that move a point on a line. So once we have one axis that can do that, we generate a second axis that can do that. So we go from X to Y, and then we create buttons for X and Y, and then we create a third axis that can do that. And then we can put a dot anywhere in space, or we could generate an entire lattice of graph paper where we can place things and name them. We digitize space. Each position is a set of digits based on these axes. All of the lattices are based on 3 axes, 3-dimensional space. So that's easy to do and that's easy to imagine. But what we want to imagine is a machine that can not only do that, but can also put dots where this machine can't. In order to do that, we need to think in terms of nonlinear machinery and non-Euclidean machinery. So these are the Euclidean perfect solids that are demonstrated by the Brovais lattices. There's 4 of them, the tetrahedron, hexahedron, octahedron, icosahedron. Okay, those are the 4 symmetries that are represented by those lattices. The one that's missing is this one, the dodecahedron. And that's kind of ironic because we can use that one to generate the other 4 pretty easily too. What we need to do is start examining our concept of a line. So a line's pretty simple. We make 2 points and then draw a line between them. Okay, now we can take this line and we can generate a circle around it. We could do that by rotating the line and making the circle, or we could hold the pin steady and rotate the space and make the circle. So we're either going to be rotating a line and generating an infinite number of points along this circle. But another way to look at a line is this. Okay, so now we generate a line that doesn't curve this way, it curves this way. So either way, we're starting with a plane and we're curving a line. We're creating an infinite number of points between 2 points. Now that's a planar representation of a line. We can do a multi-dimensional representation. If this is our line, we can imagine moving space in every direction around it. And if we move it infinitely much, we'll end up with a sphere. Okay, so one line fixed in space with space rotating around it generates an infinite set of points. They're volumetric. It's not planar, it's volumetric. Okay, well, if we imagine these, all 5 of them, as a single sphere, well, that one line, if every time we rotate, we just take a snapshot. So instead of coating the entire surface, we're taking discrete digital snapshots of space rotating around that one line. So we can see that one line with 20 symmetrical snapshots generates this. Well, once we've generated that, we've already generated this, because these 8 points are a subset of these 20. And these 4 points are a subset of these 8. And these 12 points are derivative of these 20. All we have to do is put a point in the middle of any face. These 6 points are derivative of these. So once we can build a machine that can digitize discrete sections of space with 20 points, then we can generate this, this, and this, and we can derive this and this. So all we need is a machine that will do that. And it's not so hard to do. But what we need to recognize is, while this is a superset of this, there are 5 of these inside of here, and you can see them. So if you look at any color, it's a cube. There's 5 colors, so there's 5 cubes. Now, as we break the symmetry, what we've done is, first we've taken the total infinite symmetry of space and we break it down to 20 points. When we break it further, we can break it from 20 to 8, from 8 to 4, from 4 to 2, and from 2 to 1. Well, the 1, any one of these is going to be a combination of 2 of these cubes. So this is the red and the yellow cube. Well, the 2 is the opposite one, and that creates an axis. So the yellow-red is a yellow-red axis. So this axis then, there's 10 of them. We can use that axis to rotate the cubes digitally. Okay, so now in the simplest possible configuration, instead of having 2 buttons, we have 4 buttons, and this set of 4 points will move on the surface of this object in the exact same way that a point moves on a line. So now we can get this non-linear line, and it's not so hard to do. This is an example of it. Now this one doesn't have any of the symmetry broken beyond breaking the 20 down to 4. But if we were to color these points, we could move by saying green, and let's say that's green. Red, let's say that's red. Well, the effect of this symmetry breaking from 20 to 4 is binary. So if you look down any of these points, you can see that it goes to the right of this, and when I move it, it goes to the left. So every movement, no matter what it does, it goes right, left, right, left, right, left. That's a binary relationship. So this is the most perfectly symmetrical binary number line in the universe. Okay, it uses the total symmetry of perfect symmetry, creates a binary relationship. Now there's also a binary, this is kind of like the physics phenomena of a Bloch sphere, which is used to in quantum mechanics when you're going to superimpose more than one bit. So this would be a bit and this would be a bit. Now there's another binary relationship between this and this. So when we superimpose 2 of these, we get this. Now this thing moves in exactly the same way because it's based on the superposition of 5 cubes, and those cubes then get broken down into 2 tetrahedrons. So the 5 cubes become 10 tetrahedrons. Well, that binary superposition in space becomes binary again, because there's only 2 ways to break the symmetry of a tetrahedron. You can either go black, yellow, green, blue, or you can go black, yellow, blue, green. You're always going to swap one of those 2 bits. So a tetrahedron mirrored becomes a cube. So there's a binary relationship between the tetrahedron and the cube. Now, if we want to project points into space and use Cartesian coordinates, we already have them. Okay, so we could use these Cartesian coordinates and project points into space, or we can rotate to a superposition and then do it again. Well, we can go out and back in and out and back in and rotate. We can put transpositions and rotations and superpositions together and symmetrically divide up space infinitely. So instead of just covering the surface of the sphere, we can symmetrically subdivide the interior of every sphere, as far out or as close as it is. So what we've done is, instead of projecting infinity outward, we're projecting it inward. So one sphere starting with one line can generate an infinity of spatial decomposition, which is perfectly symmetrical and programmable. So we can write scripts to reach any point we want, not just the points that are on these Cartesian systems, but we can send these points out. Instead of sending them out one point at a time, we can send them out clouds of points, or more, So when we want a point, we can collapse all these superpositions to that point. So this is more like a quantum mechanical graph paper than these three-dimensional. So instead of using 3 dimensions to put points in space, we're using infinite dimensions. Okay, we're infinitely covering space, and we can program it. We can use this machine to stepwise rotate, transpose, rotate, transpose. So think about it this way. This unit cell has one dodecahedron and one cube. Okay, that cube has cubic neighbors. So if we rotate into the 5 cubes, well, each one of these cubes basically has 26 neighbors, like a Rubik's Cube type thing. Well, it's 5 times 26. What is that, 130 neighbors? So in each one of those can create an entire universe. Oh no. Entire universe of Cartesian coordinates that are all superimposed. So you get a real dense packing of coordinates really quickly with just a few operations. So this is why I say it's universal and it's infinite. It's all based on the simple act of taking a dodecahedron and first breaking the symmetry of the dodecahedron down to a cube. So that's what we've done here. And then we take that relationship and we animate it in space through time. So now basically what we have is a symmetry operation, this rotational operation, that's not in the set of symmetry operations used to create the Bravais lattices. But we can use that symmetry operation and this simple relationship to regenerate the Bravais lattices. But we can not only do that, but we can hit every single point in between the lattices. So now we can start to imagine ways to make more exotic crystals, like a snowflake. Instead of building it from symmetry outward, we break symmetry from volumetric down to points. Okay, we can build a snowflake. We can build a quasi-crystal, basically a non-linear crystal, and we can build life. This is the general case for crystal systems. Life is the general case. So I think that life is the hardest one. Quasi-crystals are next, then regular crystals. Well, we can make a machine that will generate these points in space. So that's the whole point of doing this machine, mechanistic, programmable, universal, infinite graph paper, because we're going to program it. We're going to write a program that will hit these points, or at least operate this machine, a machine language for this simple machine. We'll do that in the next video.